Welcome to Red Dragon Mission Training number 3, Acceleration. This training will cover the following learning targets. Throughout the training, you'll be provided with example problems and questions to help you master each of these learning targets. Acceleration is the rate at which velocity changes over time. You can simply think of it as how quickly an object speeds up or slows down. Just like any variable, acceleration has its own unit, meters per second squared. Like displacement and velocity, acceleration is a vector quantity. Velocity and displacement rely on the negative sign to explain the direction of the motion. Acceleration is more complex because we're dealing with both direction and a change in velocity. The direction or sign of acceleration points where the velocity is or was the greatest. Acceleration in one direction, for example forward, is pretty easy to understand. If I speed up forward, I have positive acceleration. All of my higher velocities are in front of me, they're forward. If I'm slowing down while moving forward, as I approach a stoplight, for example, I have negative acceleration. All of my greater velocities are behind me in a negative direction. In order to understand the direction or sign of acceleration, we need to look at where those positive and negative signs are coming from. Acceleration describes the direction and the change in velocity. So if I'm talking about direction, we've already looked at this with displacement and velocity. A positive displacement or velocity is forward or up. A negative displacement or velocity has always been backwards or down. Up to this point, we only needed forwards or backwards or up or down. Now we need to look at the way velocity can change. If an object is speeding up, its velocity is increasing. It's moving in a positive direction. If an object is slowing down, its velocity is decreasing. Its velocity is moving at a negative direction. Objects can speed up, slow down, or change direction. For example, if you throw a baseball in the air, on the way up, the ball slows down due to gravity. It changes directions at the top and then speeds up on the path down. On the way up, all of the ball's higher velocities were downward or behind it in a negative direction. On the way down, the ball speeds up, so all of its higher velocities are ahead of its path. Understanding the sign of acceleration or direction of acceleration and the sign or direction of velocity can help you explain how an object moves. The direction or sign of acceleration points in the direction of the higher velocities we've discussed earlier. If acceleration and velocity are pointed in the same direction, the object's speeding up. If acceleration and velocity are pointed in opposite directions, the object is slowing down. In this case, the capsule has positive velocity, which means it's going forward. It has positive acceleration, which means all of its positive or higher velocities are ahead of the path. So it's going to speed up. This capsule slows down because its velocity is moving in a forward direction, but its acceleration is moving in a negative direction, which means that all of its highest velocities are behind it. In this case, the capsule is going to move backwards. It has a negative velocity. We know which direction it's moving. Its acceleration is negative, which means that all of its highest velocities are behind it. It has a negative velocity, a negative acceleration, but it's speeding up. Oftentimes, when we talk about negative acceleration, we assume that that means the object's slowing down. But you have to account for the direction of the object, or the velocity. Not all negative accelerations slow an object down, and not all positive accelerations speed an object up. In this case, the space capsule has a positive acceleration, which means all of its highest velocities were ahead of it, or in this case, to the right. However, since the capsule's moving the opposite direction, it's slowing down. You can compare this observation about the sign of acceleration and the motion of an object to multiplying positive and negative integers. To do this, multiply the sign of the direction, so positive is forward, negative is backwards, by the change in velocity. If it's a positive change in velocity, the object's speeding up, for example, or a negative change in velocity, the object's slowing down. Let's look at an example. An object speeding up backwards. Speeding up is a positive change in velocity. Backwards is a negative direction. Positive times negative is going to give me a negative acceleration. Opposites give you a negative. Same sign is going to give you a positive. So if I have an object that's slowing down backwards, slowing down is a negative change in velocity. Backwards is a negative direction. Negatives times negative gives you a positive. A position versus time graph is a common way to represent and interpret motion, specifically in this case, acceleration. Position is plotted on the y-axis, the unit is meters. Time is plotted on the x-axis, the unit is seconds. Velocity is the slope. So in this case, we're looking at little tangent slopes as the motion curves up. Position versus time graphs can tell us a couple different pieces of information. To find the displacement on a position versus time graph, I'm going to use interpolation. If I wanted to know how many meters I had displaced in 4 seconds, I would simply read the graph. I go over to 4 seconds on the x-axis and follow it up until I hit the graph. At 4 seconds, I've displaced about 31 meters. If I wanted to find the velocity on a position versus time graph, I would simply look at the slope. In this case, however, we have a parabola, so it's curving exponentially. There's not a straight line. Instead, I could look at little instantaneous velocities. So I could find lines that are tangent to that curve and find each of those individual velocities. In this case, the object is speeding up because as time goes on, the slope gets steeper and steeper. If I wanted to find acceleration from a position versus time graph, I wouldn't be able to. It's impossible. I would have to use a different graph. Here are a couple rules for reading and interpreting a position versus time graph. If the shape of the graph is moving up, it's moving forward. The object is moving forward. If the shape of the graph is moving downward, it's moving backwards. If it's curving towards a horizontal line, it's slowing down. A horizontal line on a position versus time graph means that time keeps moving on, but the position doesn't change. That's a stopped object. So if my motion is curving towards stop, it means it's slowing down. If it curves towards a vertical line, it means that it's speeding up. A vertical line, or a real vertical line, would be impossible on a position versus time graph. That means in one moment, so not even a whole second, but in one brief moment, an infinite amount of distance took place or was traveled. If I'm curving towards an impossibly fast speed, that means I'm speeding up. A velocity versus time graph is another common way to represent and interpret motion. I can find a couple different pieces of information from a velocity versus time graph. Velocity is plotted on the y-axis. The unit for this is meters per second. Time is plotted on the x-axis. The unit is seconds. Acceleration is the slope. If I take meters per second, my rise, over seconds, my run, I get meters per second squared as a unit. From a velocity versus time graph, I can find the displacement by taking the area underneath the graph. A common method for this is to use simple, easy-to-understand shapes like rectangles and triangles. I can find the length and width of those rectangles. I can find the base and the height for those triangles. To find the area of a rectangle, I just take length times width. To find the area of a triangle, I just do 1/2 times base times height. In order to find the velocity, I just need to use interpolation. Because it's already graphed, I'm just reading the graph itself. At 3 seconds, the object was moving about 20 meters per second. At 6.5 seconds, the object was moving about 40 meters per second. If I wanted to find the acceleration of an object by looking at the graph, I could find the slope of the line. So in this case, I have a positive slope, so that's positive acceleration. Here's a negative slope, so that's a negative acceleration. This line has 0 slope, so it has 0 acceleration. When an object has 0 acceleration, it's moving at a constant velocity. Its velocity is not changing. Here are a couple tips and tricks for understanding and interpreting the motion on a velocity versus time graph. Above the line is forward. Below the line is backwards. That middle line represents 0, so 0 velocity. Everything below it is a negative velocity, so that's how we know it's a backwards velocity. Everything above that line is a positive velocity. That's how we know it's a forward velocity. On the y-axis, the further you get away from the origin or the 0 mark on the velocity, the faster the object's moving. Everything above is moving in a positive direction faster as it moves away from 0, and everything below is moving in a negative direction or backwards direction as it moves away from 0. This means that the closer you get to the 0 mark, the slower the object is moving. This can get confusing because we see an object moving just as fast in a negative direction as it is in a positive direction. Negative velocities are not necessarily moving slower. Anytime that the motion is represented on the x-axis or where time is plotted, that object is stopped. Imagine a stop sign that moves in both directions. Everything in the center is stopped. As the lights move away from the center, the object's moving a little bit faster, and then a lot faster. Imagine you're sitting at a red light. You start to drive away. You speed up a little, you speed up a lot, and then you move at a constant velocity. My object's velocity went from 0, stopped, to a faster velocity and then stayed at that faster velocity. Imagine that you're moving backwards, but coming to a stop. So I start at my highest velocity, move to my slower velocity, and then finally come to a stop. I'm backwards, so I'm on the bottom half of the graph, moving towards the center, which is stopped. Assuming I remain stopped, I also can include a constant velocity. Acceleration versus time graphs, like position versus time graphs and velocity versus time graphs, are a common way to represent and interpret motion. On an acceleration versus time graph, acceleration is plotted on the y-axis. The unit is meters per second squared. Time is plotted on the x-axis. The unit is seconds. We don't interpret the slope in this case because the slope of all of these lines will be 0. Displacement cannot be found on an acceleration versus time graph. Velocity can be found by taking the area above or below the graph. If I wanted to find acceleration, I just use interpolation. I simply read the graph. At 4 seconds, we have an acceleration of -2. Here are some hints and tricks for interpreting an acceleration versus time graph. If an object's speeding up forward, it's above. If it's slowing down forward, it's below. If it's slowing down backwards, it's above. If it's speeding up backwards, it's below. Because acceleration is so situational, the best way to actually interpret an acceleration versus time graph or represent an acceleration versus time graph is to take the slope of a velocity versus time graph's motion. If it's a positive velocity versus time graph, it's a positive acceleration, so it's above. If it's a negative slope on a velocity versus time graph, it's below on the acceleration versus time graph. The kinematic equations are equations that allow us to predict and calculate motion. They're derived from the relationship between position in time, velocity in time, and acceleration in time. The three graphs that we've looked at give us the basis for these equations. Kinematic equation situations require knowledge of different variables. X is our displacement. A is acceleration. T is time. V is final velocity. V sub 0 is initial velocity. Final velocity is how fast the object is moving at the end of the scenario. Initial velocity is how fast it's moving at the beginning of the scenario. In many cases, the final velocity and initial velocity can be inferred if an object is coming to a stop or driving off from rest. All answers have to have proper units, and knowing the units helps you when you're organizing your given information. Displacement, or x, is measured in meters. Acceleration is measured in meters per second squared. Time is measured in seconds. Final velocity is measured in meters per second. Initial velocity is also measured in meters per second. These are the four main kinematic equations. We'll also be using a list of derived kinematic equations that make calculating a little bit more approachable. You select your base equation based on the variable that's not included. Every kinematic scenario will have three given pieces of information, one variable that you're solving for, which leaves one of the 5 variables left out, not included. The variable that's not included in the column to the right decides the equation in the column to the left. If you're using a kinematic equation derivation chart, there's 2 steps. Step 1, find the variable that's not included in your scenario. Step 2, select derived equation based on the variable you're solving for. So if you're solving for t, time, look for the equation underneath the base kinematic equation that has t by itself. For example, if you had this setup, a final velocity of 50 meters per second, an initial velocity of 0 meters per second, x is 10 meters, t is not included, a is what you're solving for. So I'm going to look, t is not included, and I'm solving for a. So I'm going to find the equation that's derived to have a by itself. Try finding the correct kinematic equation to solve this problem. X is not included. I'm solving for v, or final velocity. So I'm going to use my base kinematic equation in this case. Finding the proper equation and setting up your given information is only part of the process for solving a kinematic equation problem. Step 1, list your given variables, including the units to make sure they match up. If I'm looking for displacement, I want to make sure the value that has meters is put in the right place. Step 2, figure out which variable the problem's asking for you to solve and which variable is not included. This helps you select the correct kinematic equation. You're going to put a question mark next to the variable you're solving for or looking for, and you're going to put not included or anything else to signal that that variable, the leftover, is not included. Substitute the given values into the equation, plug in, chug. Put the proper unit on the answer and check to see if it's reasonable. If I want to see if a value is reasonable, a lot of it comes down to how big the value is, so its magnitude. If it's too big or too small for the scenario, I might want to double check my work. If you're dealing with an example of acceleration, so an object speeding up or slowing down, and you're doing a kinematic equation problem, you need to remember that the object, if it's speeding up, v sub 0, the initial velocity, should be smaller than the final velocity, which makes sense. If I start driving, I end up moving faster than I started. If the object is slowing down, the final velocity is smaller than the initial velocity. I end slower than I started if I'm slowing down. Look for some keywords like from stop or from rest or leaving a stoplight or stop sign. This means the initial velocity is 0 meters per second. It doesn't always flat out tell you. You may have to infer that value. If an object comes to a stop or comes up to a stoplight, the final velocity is 0 meters per second. This is another value that may not always be given, but may be inferred. Let's try this example problem. A car speeds up from being stopped at a stoplight with an acceleration of 5 meters per second squared. It reaches a top speed in 38 seconds. How far does the car travel in this time? On your own, try to fill in the given variables, the unknown variable, and the variable that's not included. Based on this scenario, the car speeds up from being stopped, so its initial velocity is 0 meters per second. Has an acceleration of 5 meters per second squared. It reaches its top speed in 38 seconds. Initial velocity is in meters per second, acceleration is in meters per second squared, time is in seconds. Knowing your variables helps you put the given information into the right spot. The question's asking how far does the car travel in this time. That's displacement, or x. So I'm going to put my question mark there. That means the only variable that is left over is final velocity. It's not included. On your own, given the information that we just discussed, find the correct kinematic equation. Final velocity was not included, and we're solving for x, so there's our equation. Now that we have the correct kinematic equation, substitute your given information and solve for the displacement. Remember to include the correct unit on the final answer. In order to substitute and solve for my displacement, I'm going to replace all of my variables with parentheses. We'll plug in 5 for acceleration, 38 for time. Initial velocity was 0 meters per second, and the time was 38 yet again. Now it's just order of operations. I saw right away that 0 times 38 was going to be 0, so that canceled out. 38 squared is 1,444. 1/2 of 5 is 2.5. 2.5 times 1,444 is 3,610. That seems like a reasonable distance for a car that's accelerating. However, I need a unit. That's going to be meters. Displacement is in meters.